Let's talk about vascular function. So we've talked currently about the way the heart works and the way the pulmonary system works. So now we're going to look a little bit at the tubes, all right, the veins, the arteries, the tubes that connect to the heart and to the muscles and the organs and the brain and all the other parts of the body, all right. So if you look at this picture, it's kind of just showing um, what the arterial system here on on the left would look like, and the venous system over here in the blue. Um, you know. So essentially, just from the very most basic sense, any artery. Sorry, I misspoke there. An artery is any vessel which goes away from the heart, where the flood is going, or sorry, where the flow is going uh, away from the heart. All right, it's a bit of a misnomer. Some people believe all arteries are oxygenated. For the most part, that's true. The blood within most arteries is oxygenated. The exception to that is the pulmonary artery. Oh, sorry. Yeah, that's true. And in that case, the pulmonary artery is coming from the right ventricle of the heart and is going to the lungs. It is exceptionally deoxygenated blood. That's about the least oxygenated blood there is in the body. It goes to the lungs to, of course, get oxygen. So, it's not correct to say that all arteries uh, carry oxygenated blood. Most of them do, but the true definition is that all arteries go away from the heart. All right. Um, Veins, by contrast, all veins go back to the heart. So that's the definition there. And the exception is, once again, dealing with the lungs. So if we were to look at blood vessels a little bit, okay, this is just kind of a cross section here of a typical artery and a typical vein. Uh, Arteries, as you can notice here, are much thicker. Change colors here. They're much thicker. Okay. Compare the wall sizes. And the reason for that, the reason that the walls of an artery are thicker is that they have to actually withstand pressure. Okay. Whenever we talk about blood pressure, for example, within your arterial system, that is the pressure that your blood is exerting against the walls, right? And it's fairly substantial. In arteries, um, you have a lot of pressure, so the walls of that artery have to be thicker to withstand the pressure, and also have better control of contraction and dilation and all that sort of thing. Um, for the most part, controlling arterial um, dynamics, vessel size, plays a bit more of a role than venous um, characteristics. Now, if we look at the vein, of course, it's thinner walls. Typically, it's portrayed here as just kind of being flaccid, and that's about right. Your veins can dilate quite a bit and carry a lot of blood, or they can constrict a little bit. They do have muscles in the wall. There's not really a pressure gradient within a vein. For the most part, it's just unpressurized. So that's why the walls aren't as thick. Let's get these off of there. All right. So next thing, let's look at blood pressure. So if we look at blood pressure, the first thing I want to show you is kind of the flow of things, okay, and how it relates to pressure. All right. So let's look at pressure as it relates to different phases of blood moving through your circulatory system. All right. So if we look here, this is the left ventricle. Okay. This area right here. All right. So we have pressure, and there's a pretty big flux here, right? So in the left ventricle, remembering back to cardiac characteristics and how that works, um, if if um, if at some point the heart is filling, say right here, um, after it has had a stroke, after it's had a contraction and it's ejected blood, it's then basically without much pressure in it. Okay, so if you think back to that whole cardiac cycle, after the end of the T wave, when all the blood has been ejected and it's starting to relax, okay, it's starting to distend and let blood passively flow in. What you're seeing here is this: your lowest pressure would be right at the end of contraction, right at the end of systole, and then as it starts to relax and open up, pressure is going to start building a little bit as as the um, as the blood's passively filling into it. And at some point, you're gonna have an atrial kick, and it's gonna fill up, and then once it's full, then the real pressure is going to be developed when systole begins again, and that pressure of the walls starting to close in on the blood will cause pressure to start rising up until it hits a point that it's high enough to exceed the pressure that's on the other side of the aorta, okay, your afterload, and then the blood gets ejected. Okay, so we have this pressure gets built up during contraction, and then relaxation after the blood's leaving, and there we go. That's why we have this very large change in pressure within the left ventricle. Okay, so then if we move over and we look at the large arteries, okay, we're talking femoral, brachial, that sort of big arteries. Okay. Okay. You see, now our blood pressure is, and this is just assuming normal blood pressure, 120 during systole, 80 during diastole. Okay, 120 over 80, that is the definition of normal healthy blood pressure. So that's the range there, and you can see the pressure's going up during systole. So when the heart's contracting, pressure's high. And when the heart's when the heart's relaxing during diastole, it's lower here. It's at a resting 80 millimeters of mercury. So the arteries are always under pressure. There's always pressure there. Not as much within the ventricles, right? So your left ventricle goes down and basically bottoms out during diastole. Not so in the arteries. But now, what I want you to see here, moving forward, is I want you to just follow me a little bit here, okay? So we go to the arterioles, the smaller offshoots of the arteries, which will eventually go to the precapillary sphincters, or just the very smaller vessels right before the capillaries. Then we'll get to the capillaries after things have diffused into, be it an organ or a muscle or the brain, or whatever tissue. Things have been extracted by that tissue, and it's also things have probably been given off into the blood from the tissue within these exchange areas here, the capillary beds. Okay. Then it goes back to the venules, and then that collects into the larger veins. All right. Now, what you'll notice throughout all this is high pressure goes to low pressure. Now, that's pretty basic stuff, right? I mean, we know that. I mean, if you open the door, say it's starting to get cold outside, right? Say if we're getting close to winter, say it's winter, all right. If your house is warm, and you open your front door, what has higher pressure, the outside or the inside? Does cold air have higher pressure, or does warm air have a higher pressure? Well, answer is cold air. Cold air will rush in as fast as it can because it's got more pressure. It can overcome the lesser pressure of the inside of your house, so it goes right in. Okay. And the opposite's true in the summer. Say you're using air conditioning, it's cool inside, it's hot outside. You open the door, air will rush out instead of in. So high pressure always moves toward an area of lower pressure. All right, and there's no different within the body. Okay, so If we look here, we have high pressure within left ventricle. It ejects the blood, goes to the large arteries, and then as we start getting further and further away from the heart, pressure within those vessels begins to drop, and that's a good thing. One, because they're smaller and they're probably not as able to resist force, maybe, but the big thing is we want the blood to go that way, right? That's the gradient we want to see. We want to see blood going from the large arteries down to the smaller arteries, and then to the capillaries, okay? And we want some pressure to be in the capillary beds. We don't want that to be pressureless, okay? Because then if we didn't have some pressure, then you would have a hard time getting the blood out of the capillaries and into the venules, right? So as we move along this thing, what you see is essentially that pressure is always going from high to low throughout the system, okay? And you'll see during contraction, during systole to diastole phases, you have ups and downs. The pressure goes up and down, up and down, up and down. And once we start getting closer to the capillary beds, you stop having that movement. You stop having that kind of whoosh of blood coming out during the end of systole, and then you stop having just that flux. And then eventually here, you have some pressure, but it's no longer affected by contraction of the heart. Okay, you're not seeing ups and downs. Okay, so let's talk about a term maybe we'll hear from time to time. I don't talk about it too much. I'm not really a cardiac guy, but mean arterial pressure. So mean arterial pressure is given as this term here, MAP, as sometimes it's called, mean arterial pressure, is equal to diastolic blood pressure plus 1/3 of systolic minus diastolic. Okay, so the reason we use this is it's mostly used more so in medicine. It gives an idea of perfusion. Okay, and that's a term that I feel like I should touch on because I don't know if everybody has heard this term before. Perfusion is the ability of your body to get blood to tissue. Okay, that's the simplest way we could say it. Okay, so if you're not able to get blood to tissue, you're not perfusing, we would say you're having a hypoperfusion. Hypoperfusion, at the same time, is the same word as, or is the same thing as stroke, as having a shock. If someone's going into shock, what it means is they're not getting enough blood to their tissue, which is causing that tissue to have adverse reactions, be it being unable to function, tissue death, what have you. Okay, so in medicine they'll use this mean arterial pressure. Instead of talking about systolic versus diastolic, they kind of just condense it into one term, and that gives them an idea of whether or not blood pressure is high enough within the person to perfuse their tissue. Alright, so blood pressure. Alright, so blood pressure, it's really kind of simple. I've already talked about this a little bit. It's just the pressure that's acting on the walls of an artery. Okay, and if we were to look at this in its basic components of blood pressure are this: you have blood volume, right? The amount of blood that's in the system, right? Because think about it: if you put more blood into the system, and say the artery diameter remains the same, if this diameter here, say this is the inside of an artery, if that remains constant, but I increase the amount of fluid, well then pressure has to go up, right? It's pretty simple. If I do that with any liquid in any container, the pressure within that container will increase, right? All right. So, and then the other thing is wall stiffness, okay, or tension. So arteries, the one thing that's kind of interesting about them is when you have a contraction, they're able to kind of flex a little bit. Okay, when the heart is ejecting blood, they don't maintain strictly the same size. They have, to a certain extent, the ability to flex, open up when there's that larger bolus of blood kind of moving through. um, and that helps to relieve some of the pressure. Okay. Now, sometimes through various processes, most I'd say common would be atherosclerosis, where you have that buildup of plaque on the artery walls. That reduces the artery's ability to flex. Right? It becomes very stiff. Okay, and in that case, um, it also increases the amount of pressure within the vessel. Okay, and the last little bit, and this one actually reduces pressure, or increases it, conversely. Um, if you have a smaller vessel diameter, you decrease the size of the container with the same amount of blood in it, well, pressure goes up. Or if the vessel dilates, then you have a drop in pressure. Okay, um, and that's what happens when somebody has a really bad allergic reaction. Um, what they can have is they'll have a type of shock where, or anaphylactic shock is the term. Say they're allergic to a bee sting or something, the body responds by breaking these things called mast cells. This is a tangent, by the way. Don't be too concerned about this. It's not something I'm going to ask you about. But what happens with an anaphylactic shock is when you have an allergic reaction to something, these mast cells rupture, releasing histamine. Histamine is a vasodilator. So what you get is arterial dilation, okay, and that drops blood pressure. And if your blood pressure drops too much, then you don't have enough pressure to get the blood to where it needs to go. Okay, so if it's not able to get up to the brain, then the brain loses oxygenation, and you pass out. If you're not getting it to other organs, then maybe they're not going to function as well. Certainly to muscles. Okay, so anyway, that's just an example of having extreme dilation of the arteries. So if we look at blood pressure, some of the things that you'll notice moving forward, not even really in this class, we're not going to touch on it too much, but as you go forward, and maybe you're looking at doing blood pressure during exercise, one thing you'll notice is that blood pressure goes up. Systolic blood pressure markedly goes up during exercise. Okay, this graph kind of goes through it a little bit. If you take somebody, say their resting blood pressure is 125. This is systolic, by the way. Diastolic is here around, say, 75, 80. During exercise, it would not be uncommon for that person to hit 180 or so, 200 systolic blood pressure. That would not be anything exceptionally out of the ordinary. Okay. And then during recovery, of course, it goes back down. Now, diastolic doesn't really change too much. If anything, it'll just drift down a little bit, but typically we just don't really worry about the diastolic during exercise. But this change, we can actually just, if we look back at that past equation I just showed you, looking at either it being the volume of blood, wall stiffness, or vessel diameter, we can explain why systolic blood pressure goes up. Okay. So if you want to think about it, take a second, maybe pause the video, and just a thought experiment. Okay. Of course, you're certainly welcome to just keep listening, and I'll tell you the answer. But as a thought experiment, just think about it. All right. Blood volume, wall stiffness, vessel diameter. Only speaking of the arterial system, and how would those things change during exercise, and how would those parameter changes cause an increase in blood pressure? Right. Pause now. Okay, so I'm assuming you've all taken your due diligence and you thought about it. So let's look at these. Got a few questions. Okay, so why does systolic blood pressure increase with exercise and increasing workloads? Okay, so that's what we're seeing here. We're seeing it during exercise at every stage, which would be increased workload. Okay, they're working harder and harder at each stage. Eventually they hit max. Why is their blood pressure going up? Okay. Well, there's a few things happening here. Remember what we talked about with preload? and the amount of blood coming back to the heart during exercise. As you start to exercise, your catecholamine levels increase, so you're having more epinephrine, adrenaline in your system. Okay, that is causing an increase in blood pressure because adrenaline actually causes a constriction, dilation in certain arteries. But as a net, it affects the vessel diameter. But the big thing that's doing is also working on the heart. The heart is contracting harder because it stimulates contractility. It does basically the same thing as your sympathetic nervous system. Okay. The other thing, your muscle pumps are working harder. Okay, and that's causing more blood to come back to the heart. Your veins are being constricted due to that adrenaline in the system. Okay, all those things as a net cause more blood to come back to the heart, and once that blood gets in the heart, you have more blood coming in. You get that Frank-Starling mechanism, so that the heart contracts harder, and you're getting more blood out per pump. If you're having more blood leave the heart per pump, if stroke volume is going up per pump, then that means that within the arterial system, you're getting more blood per pump, right? So you're having an increase in blood volume, right? So that's one thing. Okay, that's the main thing. More blood volume transiently, right? During diastole, you see here diastole, it's about the same, right? But during systole, as you're getting more blood in, you're getting more blood out, blood volume's going up. That's what you're seeing there. Okay. All right. So let's look at the next question. So why is a high resting systolic blood pressure an indication of possible cardiovascular system problems? Okay. High resting systolic blood pressure. Okay. So I mentioned before about atherosclerosis. Okay, atherosclerosis is of course that buildup of plaque in the artery walls. So if you're having a buildup of plaque in the artery walls and you're having a drop in the ability of those arteries to react and flex, you're getting more stiffness. You're also having a reduction in the diameter of the vessel, because if you think about it, if I were to draw a very crude artery here, if I have stuff that's just blocking, say, portions of this thing, okay, then the total amount of area here is less than it was before, right? The diameter, if you will, is less. Okay, so now we have less less space for the blood, and we have the same amount of blood being pumped out. So that's of course going to be an increase in pressure. Okay, so it's an indication of potential cardiovascular problems, because if your resting systolic blood pressure is high, it means either you're really stressed all the time and you've got a lot of adrenaline running, which is causing the first thing we talked about, or it could mean that your arteries have plaque buildup to such an extent that you're having more pressure within the artery walls, and having high pressures within the artery walls is in itself highly problematic for the cardiovascular system. And that kind of goes to the next part here, and that is, why is a high diastolic blood pressure dangerous? Okay, I'm not going to get too much into this. I cover this later in other classes, but simply put, there's a thing where if we think about this, the left ventricle of the heart, okay, the left ventricle, whenever it wants to eject blood, it has to overcome diastolic blood pressure, right? It has to overcome the pressure within the arterial system at the aorta, okay? So if your diastolic blood pressure is inordinately high, if it's very high, what happens is the left ventricle has to contract harder to get the blood out, right? But another thing happens. If there's more pressure on the outside of that, or within the arterial system, you're actually getting less blood out. So you're pumping harder to get to overcome that pressure, and then you're not getting as much blood out per pump. Okay, so that's a drop in stroke volume, and as we know from what we've talked about before, cardiac output. Okay, so cardiac output equals stroke volume times heart rate. Okay. By the way, cardiac output is often referred to as Q. Just if you see that going forward, that's what that is. If we say a drop in Q, it's cardiac output. Okay. So now let's go back here and look at this. Okay. So if I have less blood coming out per pump, because the stroke volume's going down. So if this goes down, then this has to go up to maintain an equal cardiac output. Okay, so that means not only are you getting less blood out per pump, and the heart's having to contract harder per pump, but you're having more contractions in a given amount of time. And if you're contracting more, it means you're having less time to rest. Okay, so less rest and harder contractions concurrently will cause hypertrophy of the heart, or it may cause the left ventricle to actually get thicker walls. Now maybe a couple of you out there saying, "Sweet, I'm gonna wail on my blood pressure so I can pump up and get my heart all shredded, get it all jacked." Okay, hypertrophy is good for the majority of the body. The problem in the heart, if you hypertrophy the left ventricle, what happens is, if we look at this kind of like an over the top look at a left ventricle, okay, we got these thick walls. The stuff inside, this is our area for blood, right? Cool. So if we reduce the area inside because we made the walls bigger, okay, if we do that, well, that means that the capacity of the left ventricle has just gone down. Okay, so if we can't get as much blood into the heart, then we're not going to be able to get as much blood out of the heart, which then causes your stroke volume to go down again. And if your stroke volume goes down again, your heart rate has to go even higher. Well, now it has to contract hard and faster, so you see a reduction even more because the hypertrophy is more. Okay, and then this goes down, and then that goes down, that goes up, and this process collectively we could call this left ventricular heart failure. Okay, this is something I refer to as a death spiral. It's something that, if left unchecked, will kill you, because your body, because it's trying to compensate for the increase in blood pressure, it's having these changes within the heart, and those changes within the heart become fatal if left unchecked over a long period of time. Alright, so let's look at all the factors kind of together which account for changes in blood pressure. Alright, so if we break this down, we have increased blood volume. Okay, so more blood coming into the system. Okay, more muscle pumps. Okay, so that's more blood coming back. Same thing here. Venoconstriction, respiratory pump. All these things collectively are giving us more venous return, more blood from the venous system coming back to the heart faster. Okay, so that's pretty much like, if you look at all this stuff, this is a huge key factor. The amount of blood that comes back makes a lot of difference as to how the heart reacts. Okay, so decreased parasympathetic impulses. Okay, so if you have a reduction in the parasympathetic, remember the brake paddle. Okay, if you have less of that, then you're going to get more heart rate. Okay, if you have an increase in sympathetic impulse, you're going to get higher heart rate, and you're also going to get more stroke volume. Okay, so collectively here, now we have the amount of blood coming in, and we have venous tone or venous input, right? If we have less parasympathetic and more sympathetic, well, then we get a faster, more powerful heart rate. Okay, so these factors are going to give us heart rate and stroke volume, collectively that Q, right? Cardiac output. Right. So that's one side of it. Okay. Now look over on the other side. Um, Now this is going to talk about the amount of pressure that the blood has to work against, or the kind of the afterload, right? This is more of the um, diastolic end of things to a certain extent. All right. So, increased number of red blood cells. Okay. So if you have more red blood cells in the blood, which is it can happen through like dehydration, people if they're using erythropoietin, blood doping, you can get these kind of really high blood cell counts. A lot of hemoglobin in the blood. It becomes thick. Okay, it has increased blood viscosity. It's not very good for the flow of blood. Anyway, another thing, increased body size. So if somebody becomes obese or they're just large, um, the more vessels they have, the more length of vessel there is that the blood has to flow. It means there's more uh, liquid to move. There's more resistance. Okay, so if you increase the length of vessels, you're getting more systemic resistance. All right, and then decrease in blood vessel radius. So see if you have a venoconstriction going on. Okay, so if you have a reduction in the size of the artery, if you have increased length of vessels, if you have increased viscosity, all these things give you resistance. Okay, and cardiac output, so how hard and how well the heart is working, combined with the resistance, will give you mean arterial pressure. Okay, because essentially this is more of the diastolic end of things, and this is more of the systolic end of things. All right, so let's look at the things that mediate blood pressure, okay, and flow of blood. Some people ask me sometimes, well, what's important? What should I really be focusing on? And what I tell you is, I'm a physiologist, okay, and the thing is, as a physiologist, the things that I typically care most about are the things that control other things. How does one thing affect the other? How does one thing cause a change in another? That would be the things moving forward. Next few slides, okay? So, chemoreceptors, mechanoreceptors, baroreceptors. These things allow, or they take up and take stimulus from various factors, and they directly cause changes in the cardiac response. Okay, so let's look at them individually. A chemoreceptor, I think we've talked about these before. Once again, think of chemistry, receptor, chemistry. So metabolites. These are metabolic byproducts. Okay, so located within the central nervous system, within blood vessels and skeletal muscles, you have chemoreceptors. Okay, and in our case here, they're receptive to CO2. Okay, that's a byproduct of metabolism, right? Oxidative metabolism, Krebs cycle. Okay, changes in pH, also, that's coming from metabolism through many of the different systems, muscle contraction. Okay, potassium and others. Okay, these are the main ones. Okay, so when these things are detected in blood flow, you have an increase in Q, cardiac output. Okay, blood flow indirectly could increase diastolic blood pressure. Okay, now if we look at mechanoreceptors, think of mechanical. Okay, mechanoreceptors deal with sensing stretch or tension within walls. Okay, so these are mostly within the heart, also some in skeletal muscle. And anyway, when you have a increased stretch within the heart, we've seen this with the Bainbridge reflex. You have an increase in cardiac output and the characteristics or the performance of the heart. And then baroreceptors. Baroreceptors deal with pressure. Here I want you to think about, when you see baro, think of barometric pressure. So baroreceptors deal with pressure, right? So these are found primarily in the carotid body, which is, think of carotid arteries, okay? So, and also within the aorta. You'll see these as well. But baroreceptors, mostly they're leading up to the brain, right? Because the carotid arteries go to the brain, right? That's what feeds the brain with blood. And it's very important that your blood has sufficient blood flow, of course, because if it doesn't and the brain isn't getting fed, well, then nothing else in your body will really work for very long. So, um, if you have a drop in pressure, as we'll see in the next slide. So here's the baroreceptor. Okay, so like I said, the baroreceptor is located within the aorta and the carotid arteries. So um, those are of particular importance because it's kind of a feedback, if you will. Okay, so when you're pumping blood out, when there's a certain amount of pressure within the arterial system, your 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 brain, okay, the heart, to a certain extent, need to have feedback. Am I doing enough? Am I doing too little? Am I doing too much? All that sort of thing. Okay, so what happens with these baroreceptors is they detect pressure within the artery, and if say pressure is too high, if there's too much pressure, see, if pressure increases too much, it notifies the central nervous system, and then impulses are sent to decrease heart rate, decrease cardiac output, which will lower blood pressure. Now, if blood pressure is too low, then what you'll see is notification to increase heart rate, increase cardiac output, increase blood pressure. Okay. Now, that's just a normal response. Okay, and you can see this if you're one of those people who when you sit down or lay down, you stand up really quick and you maybe not like fully black out, but like maybe you're just a little dizzy or your eyes black out a little bit, distorted vision. What that's called is orthostatic hypotension. It's a mild syncope if you're not actually passing out, and it's very common. But what that is just the inability for you to perfuse the brain for a second. Okay, the inability for you to get blood up to the brain will cause that kind of passing out sensation. Okay, and what will happen pretty quickly, within seconds, is you stand up, pressure is too low within the carotid arteries. Okay, so you're going to feel that sensation of, whoa, what's going on? I gotta, sit back down or something. And your heart will immediately then go, okay, we got to work harder to get the blood back up there. And you're going to see an increase in pressure, and you'll see an increase in heart rate. Okay, so I mean, it's kind of hard to plan for, but if you can consistently reproduce that sensation, take a heart rate or take a blood pressure when you're laying down, stand up real quick, get a little dizzy, do a blood pressure. You'll see a pretty decent difference. What should be noted with atherosclerosis, when that buildup of plaque in the arteries, is with a decrease in wall stiffness, you also have a decrease in the sensitivity of baroreceptors, which is why people who have unhealthy cardiovascular systems suffer from fainting and strokes and difficulty with regulating pressure to the brain. These are the people who really do need to kind of take it easy and ease their way into standing up and sitting down and all that sort of thing, because they have a hard time regulating blood pressure rapidly. Blood flow distribution. All right. So, simply put, when we start to exercise, there's a shift in where blood is going throughout the body. Okay. So, as we start to exercise, let's say I want to look at this. Okay. So this is the resting side here. Okay. Look on the bottom. This is resting during heavy exercise. Okay. So let's look at workload. Okay. Cardiac output. So the cardiac output, our Q right here, is 5 liters per minute, and up here our Q is 25 liters per minute. So this is 5 times more work. Okay, so if and that's not even nearly what a human's capable of as far as the upper end of performance, but let's just say, fine, that's what we're doing. 5 times more blood is moving through the body. Okay, what this means is, if we look at the resting here, per minute, the heart is pumping 5 liters of blood. Up here, per minute, the heart is pumping 25 liters of blood. Okay, a lot of blood. So, anyway, let's look at this. So during rest, if we look at all the blood, most of it, okay, most of it is sitting in the gut. Okay, it's in your organs, it's in your digestive system. If we take this plus your kidneys, I mean that's almost half of all the blood in your body. That's where it's getting shunted to. Because when you're resting, what are we doing? We're eating food, we're digesting food, we're filtering blood. We're not really, we don't need to have a ton of blood going to the muscles. We don't really need it going anywhere else. It's going to the brain, of course, because the brain always gets fed. The heart's not working super hard. It doesn't need too much. Okay? Bone's getting a little bit, skin's getting a little bit, muscles getting a little bit. Okay? But these are really the things that change right here. The amount that's going to the kidneys, and then your gut. Okay. So then if we go up here and we look at during heavy exercise, we go from 20 to 25% to 3 to 5%. Heart, interestingly, is still getting the same percentage of blood. Percentage. Okay. Now remember, you're working 5 times harder. So if you're, say down here, this 4 times 5 gives you 20. Up here, 4 times 25 gives you 125. Okay, actual flow. Right? That's the actual amount that's getting there. So it's still quite a lot of flow, but it's by percentage about the same. Right? Oh, sorry, my math's all wrong there. What is 125? Just 100. Okay. And that, fellas, is why I am not a mathematician. Okay, so moving on, we see the kidneys similarly take a pretty big drop in percentage. The bone, once again, the bone doesn't really need a lot of flow during exercise. The brain, look at that, we're getting less flow to the brain. Once again, though, let's kind of break this down a little bit. If we take during rest, we have 15 times 5, right? 5 liters, 15. Up here we have 25. Okay, we have 25 liters. And this is times, say, 3. Yeah. Let me change the order of those so it's more apparent. Okay. All right. So if we do this, we're getting 75, right? And if we do this, we're getting 75. Right? So it's actually the same amount during exercise, during heavy exercise, and during light work or rest. And the reason being is, as you start to exercise, your brain doesn't require more blood. It's not working harder. It needs the same amount. So it gets about the same amount. Okay. If we look at the heart, the percentage doesn't change because as you start to work harder, the heart actually does need more blood. It needs to contract harder and faster, and that's causing those muscles to need to be supplied with more blood. Okay. So, moving on down the line, you're getting very little flow to the skin. Okay. But look at this. 80 to 85% of your blood is getting shunted directly to the working muscle. Okay? That's a lot. That's a ton. Right? This is depicted here. Approximately 20 liters per minute of blood going directly to the muscle. During rest, less than 1 liter is getting shot to the muscle. Right? So, it's kind of cool the way your body adapts and changes, or accommodates rather, your activity. Okay, your body is designed to be able to do a multitude of things, but one of those things it's designed very well for is exercise. Okay, and when you start to exercise, one of the major things it does is it prioritizes keeping those muscles going, keeping the heart going. And that way, presumably whatever you're doing, the reason you're running really fast, maybe there's a a wild animal after you that's trying to eat you. It's from a survival perspective, it's very important that you're able to keep going, and that's the thought maybe behind why you're getting so much good adaptation, or so much good accommodation toward exercise, or when you exercise within the cardiovascular system and really all the systems. But here it's just very easy to see. It's a very readily apparent thing. There's three levels of control that will really determine, along with that whole idea of um, of more blood going to the muscles, more, say the same amount going to the heart. You know, we're having changes in the vasculature which accommodate that. Okay, the first level of control is at the artery. Okay, the arterial, the bigger vessels coming away from the heart. Okay, those are the ones that are going to give us our first level of determination of where blood goes. Okay, and those are affected mostly by catecholamines. Okay, so epinephrine. When you start to exercise, epinephrine levels will increase. We're going to talk a lot more about that in the in the coming unit, fourth unit. But for now, let's just stick with this. Adrenaline goes up as you start to exercise. Harder and harder you go, the more adrenaline hits your system. All right. So when adrenaline hits your system, it reacts with arteries, and it reacts with things called adrenergic receptors, which there's different types of. Okay, so depending on where the epinephrine is received, on what kind of receptor, it's going to have a different response. Okay, so if we look at this, alpha receptors, alpha adrenergic receptors, and there's multiple kinds within this, but just say alpha for now. They cause venous constriction, and they're more sensitive to norepinephrine. Norepinephrine is like the brother of epinephrine. They're both catecholamines. All right. So you have constriction happening with that, and then beta receptors cause vasodilation, and they're more sensitive to epinephrine. So it's kind of interesting. You have depending on which catecholamines more prevalent in the system and where it's being received, you're having both maybe dilation or constriction. And questions come up sometimes. Well, if they're both, one's dilating, one's constricting, what's happening? Well, it's not that simple. Kind of the interesting thing is, as a muscle starts to work, it sends out these like trophic factors, these minor factors that are kind of local, and so they don't hit the bloodstream, but they do kind of perfuse through tissue. And as I understand it, because once again I'm not a cardiac guy, but as I understand it, these factors cause an increased expression of differing types of adrenergic receptors. So let's say I'm cycling and my legs need more blood. What'll happen is I will have systemic constriction, except when I'll have more receptivity here, say throughout most of my body. But when I start to exercise, my quads want more blood flow. These beta receptors become more sensitive around the area of the quad, and because they become more receptive, they will start to open up the arteries directly relating to those muscles. Okay, only in that area. They don't open up all of them, right? Because then I'd go into shock and I'd have a hard time perfusing anything. So instead, what you see is you have an increase in the diameter of the vessels that go to the working muscle, and it has to do with, like I say, the interplay between these receptors and epinephrine. And because you have an increase in dilation there, pressure starts to drop. And if we go back and we think about it, if pressure drops in an area and there's higher pressure around it, then you're going to get more flow there. Okay, so you're going to get an increased amount of flow to the area of low pressure. Well, you dilate only the area that's leading to the muscle, means that muscle that's working is going to get more flow, it's going to get more traffic of blood. Okay, So the second layer of control is at the smaller arteries, the arterioles, and this is where we're starting to get toward exchange vessels, but we're not there yet. Okay, and these guys are influenced primarily by things like heat, nitric oxide, ammonia, lactic acid. Okay, so this is more like fine tuning. Okay, because I was kind of talking a little bit before, like, hey, you know, when adrenaline hits the system, it starts to dilate the major arteries. Well, now go to these specific areas. When you have more heat, more nitric oxide, ammonia, lactic acid, these things cause the arterioles to dilate. Okay, so let's think about this. During exercise, why would a working muscle be hotter? Why would it have increased heat? Okay, nitric oxide we haven't talked about, but exercising causes an increase in nitric oxide locally. Where do we get ammonia from? Okay, these two things go back to the first unit, and well, no, sorry, second unit, and then lactic acid, same thing, metabolism. Okay, heat. Okay, whenever we break down ATP, of course, go to ADP, but we're also getting heat from that, right? Right. So whenever you're breaking down ATP, you're producing heat. That's why working muscles are hotter than the other parts of the body. Okay, so if that area is hotter, you're going to get more dilation of these arterioles. Okay, when you're working, you're getting more nitric oxide, which also is a vasodilator. Ammonia. If you remember back to immediate system, okay, in the immediate system we talked about ways of maintaining AMP concentrations. Well, one of those things was when you start producing a lot of AMP, the body will break down, or the muscle cell will try to reduce AMP concentrations by employing an enzyme called AMP deaminase, and the net result of that equation is ammonia production. So when you work out really, really hard, remember we're depleting at this point, if we're producing ammonia, we've depleted the immediate system. We've worked really hard. That will produce ammonia. Ammonia hits the bloodstream and causes more blood flow to start coming to the area. It's a feed-forward system, right? If you start depleting one system, the metabolites from the systems are actually causing the next one to start working better. In this case, if you're having heat, ammonia, and lactate coming from, of course, glycolysis, if these things are starting to build up, it means you're working really hard. And as you're trying to shift over to steady state or more, you're going to need more blood flow, right? Because you need more oxygen for the oxidative system to work. You also need more carbohydrates, you need more fats, and you need more substrates to go to the area. And importantly, you also need to be removing carbon dioxide that's coming from that system, right? So you need more flow. So it's very kind of cool that all these things are feeding forward, right? Ammonia production, lactate production, heat, nitric oxide, all these things as you're exercising are kind of triggering the next thing to work well. So on with that line of thinking, the third level of control. This is at the precapillary sphincter. So if we work our way down, if we go from arteries down to arterioles, and then right before the capillary is often referred to as the exchange vessels, so at the capillary bed you have these sphincters, okay. And the reason being is most of the capillary beds in your body, a lot of them, they just stay closed all the time, okay? Because if they're always open, there would be too much blood going everywhere, okay? You wouldn't have enough blood to fill all the capillaries at the same time. So for this reason, as you start to exercise, you have to open up the capillary sphincter to get blood into the area, okay? So, and there's some implications to this. We'll think about it in a second. But precapillary sphincters are the last level of control, right? So as we're looking at this, let's look at the factors which cause that precapillary sphincter to open. CO2, hydrogen ions, heat. Okay, 100% derived from metabolic activity. So simply put, if a muscle starts to move, if it starts to work a lot, it starts producing heat, carbon dioxide, hydrogen levels start getting high, the capillary beds around that muscle will then open up. And if they open up, it means you're getting more oxygen flow, you're getting more substrates, you're getting more metabolite removal, all that stuff. Okay? And that's very cool. It allows you to fine tune, allows the body to fine tune exactly where the blood's going. Okay? But I want you to think about something else for a second. Okay? So when you start to exercise, if you're doing a set of, I don't know, 8 to 12 repetitions, decent weight lifting, you do it a few times. What happens to your muscles visually? How do they feel? Okay, they get a pump, right? You guys have probably heard the pump, right? Well, part of that pump sensation is the fact that as you started to work out, the capillary beds around that muscle have opened up, so you have more blood flow, you have more liquid, you have more stuff in that area. So they feel bigger, the muscle feels bigger. Muscle hasn't changed, you just have more blood there now. That's why a lot of those, they have these drugs where people can look, or not drugs, but supplements they call them, where you can take them and they'll give you that pump look all the time, so you can look bigger than you are chronically. Well, a lot of those things, they'll have, like, nitric oxide will be one of the major things. All right, and what that does is just opens up vessels. So if you have an agent in your system which is opening up vessels, then you're getting more blood flow to the area, and it just gets a little bit bigger. That's pretty much all there is to that.